Okay, to pick up where we left off in the first part, we continue with base ionization. Bases, like I said, ionize in water also. And like with acids, strong bases ionize completely 100%, and you'd use a one direction arrow. And weak bases only ionize partially, and you end up with an equilibrium situation. So you'd use the double-headed arrow. Like with acids, there are only a handful of bases that are strong bases, and the rest are all considered weak bases. And so the best approach would be just to remember which acids are strong and assume any others are weak. First of all, the strong acids are all metal hydroxide, or all of them are metal hydroxides. But there are only a few metal hydroxides that are strong bases. There are dozens of other metal hydroxides that are weak bases. Okay, so the metal hydroxides that are strong bases are the metal hydroxides of the metals in groups 1 and 2A, except for the 2 at the top of 2A. So that would be lithium, sodium, potassium, rubidium, cesium, francium, calcium, strontium, barium, presumably radium, but that's radioactive, so nobody really wants to play around with radium hydroxide. But those are the strong bases. Those are the ones that ionize 100%. So here's the list again. Keep in mind that in group 2, the metal ions always take a charge of +2 in their compounds, and therefore it takes 2 OH- hydroxide ions to balance out the charge. So calcium hydroxide is Ca parenthesis OH parenthesis 2, for instance. And that means that each molecule of calcium hydroxide has 1 calcium ion and 2 oxygen atoms and 2 hydrogen atoms in it, in the form of 2 OH groups. Unlike acids, strong base molecules, or no, actually metal hydroxides anyway, are all ionic compounds. Actually, even the weak metal hydroxide bases, like say iron hydroxide, that's a metal hydroxide, but it's not one of the strong bases, so it would be a weak base. And all of the metal hydroxides are ionic compounds. It's just a matter of how soluble they are in water and whether they ionize completely or incompletely. But they are at least ionic compounds, so it makes sense that they should ionize in water. Some of the ionization reaction doesn't actually require the participation of H2O because the OH- ion doesn't grab onto any of the H2Os in the solution. They're just sort of there and independent of everything else. And so the ionization of sodium hydroxide, once you dissolve it in water, it becomes Na+ and OH-. The OH- being a polyatomic ion, as is usually the case with polyatomic ions, the OH- does not come apart itself when the compound dissolves in water. The OH- comes apart from the Na+, but the O and the H stay together. So it's OH-. Barium hydroxide has a formula BaOH2, and so therefore when it dissolves in water, you get Ba+2 as an ion and 2 OH-. Because each molecule of barium hydroxide has 2 hydroxide ions in it, barium hydroxide is also known as a dibasic base. Dibasic because it gives you 2 OH-. On the other hand, a weak base like copper hydroxide, copper 1 hydroxide to be rigorous about it, would ionize to some extent in an equilibrium reaction. And for each one of them that does ionize, you get a Cu+ ion and an OH- ion. But most of them do not ionize, and most of them will be present as intact CuOH molecules. Ammonia is probably the most commonly encountered weak base. And if the base doesn't have hydroxide ions of its own, then the water molecule actually is involved in the ionization. So in a case of a weak base like ammonia, NH3, you do need to write in the H2O to show how it ionizes, because what happens here is that the ammonia takes in an H plus from water. And when you take an H plus away from water, you know, water is HOH. So if you take an H plus away from water, what's left? OH minus. And that's why ammonia is a base. It doesn't release hydroxide ions of its own because it doesn't have any, but it does react with water to form OH minus ions. And this is known as hydrolysis, basically when the H2O itself is involved in the reaction. Okay, so we have a question here. What is the OH minus concentration of 0.34 molar KOH? Well, KOH is potassium hydroxide. Potassium is right there in group 1 of the periodic table. Therefore, potassium hydroxide is a strong base and will dissociate completely. And that means that the final hydroxide concentration will be the same as the initial concentration of the base, which in this case is 0.34. And now they want to know, what is the OH minus concentration of 0.34 molar barium hydroxide? And in this case, the dissociation is complete. Barium hydroxide is a strong base, but each barium hydroxide molecule gives you 2 OH minus ions. So you can set up a little table here if you want to make sure that you're doing everything correctly. But if you start out with 0.34 molar concentration of BaOH2, and each BaOH2 gives you a Ba+2 ion and 2 OH minus ions, and you're starting with none of either of those, you know that this is a reaction that goes to completion because barium hydroxide is a strong base. And so you're going to use up all of the barium hydroxide. You're going to lose 0.34 molar of it because that's what you started with. By the stoichiometry of the reaction, you're going to be gaining products, and for the barium ions, you're going to gain the same amount as you lost for the barium hydroxide because there's 1 barium ion for every barium hydroxide. So this should be 1-to-1. It's just that you're gaining barium ions and losing barium hydroxide. But for the OH minuses, notice there are 2 of them for each molecule. So you're going to be gaining hydroxides because they're products, and you're going to be gaining twice as many as you lost for the barium hydroxide. So for the hydroxide ions, it's going to be +2 times 0.34 or 0.68. So what you end up with for the hydroxide ion concentration is 0.68. And that would be the answer here. Okay, there are various theories that explain the behaviors of acids and bases because flaws have been found in previous theories. And so that's what we do in science. You know, if you find a flaw in a previous theory, you reformulate it. And if you're the guy who reformulated it, then you get to put your name on it. And that's what happened with the Brunstad-Lowry theory. In 1923, they revised the Arrhenius acid-base theory, accounting for some of the gaps in his theory. It turns out, you know, there are some compounds that can act as bases, even though they don't qualify as bases under the Arrhenius theory. And in fact, ammonia is one of those. And the Brunstad-Lowry theory has the advantage of explaining those situations in a way that basically doesn't have any other disadvantages to it. And it also brings in the idea of acid-base pairs, which is very useful for reactions that could be reversed. So we'll look at those too. The Arrhenius theory basically, the Brunstad-Lowry theory basically says that an acid is a proton donor and a base is a proton acceptor. Remember, of course, that a proton is an H+ ion. And so this is actually, it sounds similar to what Arrhenius said, and you know, it is similar, but it's actually quite a bit broader. This takes in quite a bit of situations that the Arrhenius theory didn't. Like, for instance, ammonia. in this case here, Arrhenius said that that a bases basically increase the hydroxide concentration in water by releasing their own hydroxides. And ammonia, of course, doesn't have any hydroxides. So by Arrhenius' theory, ammonia can't be a base, but yet it is a base. And it turns out that it increases the hydroxide ion concentration in water by reacting with the water itself and taking away an H+, which leaves behind an OH-. And all these free OH- in solution make the solution basic. So ammonia is a base. Only it didn't fit the definition under Arrhenius. It does fit the definition under Brunstad-Lowry. Okay, the Brunstad-Lowry theory also includes the concept of conjugate acid-base pairs. So this is what I was talking about a moment ago. And this is related to the proton donor acceptor idea, which is actually kind of similar in concept to the idea of the electron donor electron acceptor when you're talking about redox reactions, oxidation reduction. And that's because when you're talking about oxidation reduction, that electron has to go somewhere. Whatever compound it is that loses the electron, it's not going to give that electron up unless the electron has a place to go, some other compound that will take it in and accept it. You can't have free electrons sitting around in solution. And that's a very similar thing is at play in acid-base reactions. An H+ ion is not going to be released by an acid unless there's something else there that's willing to take it in. And that something else may be by default, might be the water, that's the solvent, but something's got to take that H+ ion in. Okay, so like I said, if no other reactant is present to accept or donate a proton, and the same goes for donating a proton, if there's a compound present that really, really wants an extra proton, and there's nothing there that would normally be considered an acid that want to give up a proton, then water can actually do that. And water can give up the proton, in which case water is acting like an acid. And so it turns out water can actually act like an acid or a base if it's in the presence of something that's the opposite. So if you put a base in water, water can act like an acid. If you put an acid in water, water can act like a base. And it really depends on whatever it needs to be to satisfy the other guy. Okay. And that is known as being amphoteric because it can go either way, kind of like an amphibian. Water can donate a proton or accept a proton, and that makes it amphoteric. And examples of that include, well, the ionization reactions for acids when you write the H2O in. So we put HCl in water, and we get H3O plus and Cl minus. If you can read what I've written here, hopefully, I've written proton donor under the HCl, because you notice what happens is the HCl gives a proton to the H2O, and the H2O ends up as H3O plus, that is H2O with an extra H plus, and the HCl itself ends up as Cl minus. That is, it's lost its H plus. So HCl in the forward reaction is a proton donor, and that makes it an acid, which is pretty good because hydrochloric acid better be an acid. On the other hand, H2O, we don't normally think of that as a base, but it is taking in a proton from the HCl and becoming H3O plus. So the water is a proton acceptor, which makes the water, in this case, in the forward reaction, a base. And then we just noted what each substance becomes after the reaction. The HCl becomes Cl minus, and the H2O becomes H3O plus. And those are what are known as the conjugate acids and bases of the reactants. So HCl starts out as an acid donating its proton, and it becomes Cl minus, which is the conjugate base of HCl, conjugate in the sense that they go together. And Cl minus is a base in the sense that if you did the reverse reaction, look what would happen. Cl minus would be taking a proton away from H3O plus and becoming HCl. Well, when the Cl minus takes in that proton to become HCl, it's accepting a proton, which makes it a base. in the reverse reaction. If you look at H3O plus, if the reverse reaction were to occur, the H3O plus would be giving up a proton to Cl minus, and H3O plus would be becoming H2O, and the Cl minus would become HCl. And by giving up that proton to Cl minus, H3O plus is acting like an acid. So therefore, it's the conjugate acid of what it was before, which was the H2O. So you've basically got an acid-base reaction going on in both directions. All right. You can look at the same kind of thing with something like ammonia. Say ammonia and H2O will yield NH4 plus, the ammonium ion, and OH minus, the hydroxide ion. And looking at the forward reaction, NH3 plus takes a proton from water and becomes NH4 plus. So NH3 becomes NH4 plus. In doing that, the NH3 accepts a proton, which makes NH3 a base. And the fact that the H2O gives that proton to the NH3 and becomes OH minus makes H2O an acid in the forward reaction because it's donating a proton to NH3. If the reverse reaction were to occur, and that is a real possibility in this case, in fact, the reversal reaction is occurring in this case because it's an equilibrium, then in the reverse reaction, if you look at what happens, the NH4 plus loses a proton and becomes NH3. Well, because it gave up a proton, that means NH4 plus must be an acid in the reverse reaction. And the OH minus, well, OH minus is always going to be a base anyway, but OH minus gains a proton, takes in a proton from the NH4 plus and becomes H2O. So the OH minus is a base in the reverse reaction. All right. And as I mentioned a moment ago, water can be either an acid or a base according to the Bronsted-Lowry theory. It really depends on what the other substance is. If you have substances that are generally recognized as acids or bases together dissolved in water, then water doesn't usually get involved one way or the other. Like if you have HCl plus NH3 together in water, then they will react with each other and leave the water out of it. But if it's just an acid or a base in the presence of water, then the water essentially becomes the opposite of whatever substance you've added to the water. So if you add an acid to the water will act like a base. If you add a base to the water will act like an acid. Okay, and that's because of the autoionization reaction of water, which we'll talk about in a little while, which is H2O dissociating into H plus and OH minus. So water has H plus ions that it can give up and become OH minus. So water can act like an acid. Water also has, because this is an equilibrium reaction that's always going on whenever you have water. You'll also have some H plus ions and some OH minus ions to some extent. The OH minus ions can take in an H plus and become H2O. And so that's basically water acting like a base. Whoops. All right, so what we're going to do here in this example is see if we can classify each species as a BL, that is Bronsted-Lowry acid, or Bronsted-Lowry base, and identify the conjugate pairs. So if you've got SO4 2 minus, the sulfate ion, and water in equilibrium with HSO4 minus, that's the hydrogen sulfate ion, or bisulfate, and OH minus. The SO4 minus, 2 minus, the sulfate ion, if you look at what happens to it, it gains an H plus. So the SO4 minus 2 ion is a proton acceptor. And that makes it a base, a Bronsted-Lowry base. That H plus that the SO4 minus 2 gained came from the H2O. That means in the forward reaction, the H2O is an acid, a Bronsted-Lowry acid. And so there's your Bronsted-Lowry acid and base. And during the course of the reaction, the SO4 becomes HSO4 minus, So that's the conjugate acid of the Brunstad-Lowry base in the forward reaction. And H2O becomes OH minus, which is the conjugate base of H2O in the forward reaction. You can also look at it as what happens when the reverse reaction occurs. Well, the HSO4 minus loses a proton to become SO4 minus 2. So in other words, the HSO4 is donating a proton. That makes it an acid in the reverse reaction. The OH minus becomes H2O by taking in that H plus from the HSO4 minus. That makes OH minus a base in the reverse reaction. And so now you have your conjugate acid base pairs. All right. And the second part of the example is HSO4 minus, that is the hydrogen sulfide ion itself in H2O, and it goes to SO4 minus 2 and H3O plus. Essentially, this is the same reaction we just had, only in reverse. So we get to sort of explain the whole thing all over again. HSO4 minus becomes SO4 minus 2, and so that is a conjugate acid base pair. And H2O takes in an H plus ion from the HSO4 minus and becomes H3O plus, so that's the conjugate acid base pair. In the course of the forward reaction, the HSO4 minus gives up a proton to the water. So that makes the HSO4 minus a proton donor. That makes it a Brunstad-Lowry acid. The H2O takes in that H plus from the HSO4 minus, meaning that H2O is a proton acceptor or a Brunstad-Lowry base. In the reverse reaction, the SO4 minus 2 would be gaining a proton, so accepting a proton from the water, which makes that the SO4 minus 2 ion a base in the reverse reaction. And the H3O plus reaction, of course, is where that proton comes from that the SO4 minus 2 gains. And that means that the H3O plus ion is an acid in the reverse reaction. Okay, so that's it's sort of an introduction to conjugate acid base pairs. Next, we're going to do conjugate acid base strength, which we don't really have time for in this video, but we'll start with that next time. Because it turns out that conjugate acid base pairs tend to be relatively opposite in terms of strength. So for instance, H3O plus, is a really strong acid. And so the conjugate base is really weak. H3O plus is really strong as an acid. H2O is really weak as a base. And it tends to go like that with conjugate acid base pairs. But we'll get into that in more detail next time. So until then, I'll see you later.